So, how the design and the optimization studies were carried out for the first line. So, electrical line parameters was similar to 765 kV single circuit line. This was for when the line were thought for the double circuit. So, what was the optimization which was done and how the idea was used for the similar idea for the single circuit, that is AC is a single circuit, DC is a double circuit. So, design optimization for 765 kV double circuit transmission line was with reference to the single circuit line data which was available. So, the nominal voltage again 765 kV and maximum operating voltage was 800 kV. Switching surge was similarly in a single circuit 1550 kV peak was employed. The air gap clearances 5.6 meter at 0 degree, 4.4 meter at a swing corresponding to 2-year return period and 1.3 meter at swing corresponding to 50-year return period was adopted. And conductors bundle alternatives which were employed for the double circuit, again the data was from the previous single circuit lines, and here the adoption for double circuit was they have adopted quadrupole, that is a 4 conductor ACSR all aluminum steel reinforced mousse conductor. The mousse is 31.77 is the diameter of the conductor, 4 being 4 conductors of 31.77 dia were used when the mousse were employed. Similarly, many alternatives were tried out. They have also used quadrupole, that is a 4 ACSR Bursimis conductor, again Bursimis being 35.05 mm. Further lap wing conductor of 38.2 mm dia, zebra of 28.62. Here they use 6 conductors. You can see the hexagonal arrangement of zebra conductors with dimension of 28.62 was employed. Similarly, hexagonal ACSR cardinal conductor of dia, cardinal conductor is 30.4 mm dia, and further hexagonal ACSR mousse conductor was also tried out. So, several of this combination with 4 conductors here mousse, there is a quadrupole what we call, with the hexagonal arrangement also was tried out for the better optimization. So, studies were conducted for double circuit and lot of data was available, so that before the actual construction of the tower and before actual stringing, this has helped for the proper optimizing the various combinations. So, design and optimization which was carried again for 765 kV double circuit transmission line gives the values maximum surface gradient which is given here kilovolt per centimeter, and fair weather corona onset voltage kV per centimeter. So, this is maximum surface gradient, this is clean condition the onset, that is a inception corona gradient which is in kV per centimeter. Again for various type of conductor alternatives, that is using a 4 conductor quad mousse type of conductor, quadrupole Bursimis, quadrupole lap wing, hexagonal 6 conductor zebra, 6 conductor cardinal or hexagonal mousse type of conductors. Several of these options were tried out, and you can see the surface gradient studies which have been conducted show the values from 21.2 to 16.2 kV per centimeter, and the corona onset gradients were seen to be anywhere between 19.7 to 20.1 kV per centimeter. So, further the electric fields were also tried to study these electric fields with various again conductor combinations were tried to see, and the values which are reported here, the maximum electric field within the right of way in kV per meter, and electric field at right of way edge, what was the edge. So, within, inside and outside at the edge the values are given for various conductor configuration. So, for mousse with 4 conductors 9 kV per meter, in case of Bursimis again it is 9, lap wing it is 9.3, the hexagonal zebra it is 10 kV per meter, further cardinal and mousse also have given the similar values of 10. Here the repetition of electric field at a right of way edge in kV per meter gives anywhere between 1.6 or 1.4 in case of Bursimis, which is slightly higher diameter conductor. Lapping becomes much more, but the value shows 1.5. Further hexagonal arrangement, the right of way edge, the electric field estimated was seen to be 1.9 kV per meter. So, these are the design and optimization studies which have been carried out for double circuit 765 kV transmission line. So, this gives the line diagram of the tower configuration of 765 kV DC tower which has been used. So, you can see the total height and the maximum sag which would be, and the minimum clearances and number of conductors which are employed, the hexagonal type of arrangement you can see, and what is the minimum clearances from the ground to the phase metal part, that is a tower edge, minimum of 4.5, and the ground to ground is 23.5 meters. So, this is how the typical 765 kV double circuit tower configuration was designed or estimated for the construction. This is again same first project which was executed from the Kishanpur to Moga, the 765 800 kV horizontal configuration. These were the first towers which were constructed with 85 meter right of way various tower configuration. So, in towers we have different types A, B, C, D and various configurations. So, this first shows the tension arrangement, V suspension string, here it shows the tension arrangement. So, these are various configurations for 800 kV of tower type A. This is a tower type A and this is a tower type D. So, various configuration for a single circuit transmission system. This shows 400 kV a double circuit. You can see double circuit again R, Y, B or 3 conductors in one arm, 3 more conductors on other side. So, this is entire thing is single circuit, one more circuit, double circuit, each phase again consisting of 4 conductor bundles. So, that is what quadruple bundle in. So, this entire 4 conductor bundle forms a single phase. You have 2 circuits here. This is again a tower configuration for 765 kV single circuit with horizontal configuration as shown. This is a typical delta type of configuration again for the 765 kV. So, a lot of modifications, design aspects have been carried out over the period, and the optimization has been done. This is mainly to see the right of way which is 85 meters which is required for a 765 kV could be reduced. So, the tower configuration, the advances in the technology going in for different towers have also parallelly happened. A lot of work has been conducted in this to reduce the overall weight, the economy and also the distance, that is a right of way, has been carried out. So, this is again an example of delta vertical single circuit tower here. This is again a delta vertical arrangement for a double circuit tower. This is important, the present transmission system in the country is being witnessing a lot of advances are happening. So, we are talking about the 765 kV transmission in the country. So, now the power requirement has drastically gone up. So, a lot of long distance transmission both at ultra high voltage AC and ultra high voltage DC lines are being constructed and several advantages in going for a long distance DC transmission. So, 800 kilovolts DC lines are being constructed across the country, and DC and AC transmission of 1200 kV also is being thought for last 4 to 5 years. Presently, we have an experimental facility at Bina in Madhya Pradesh where 1200 kV test line is being energized, and this facility in conjunction with the power utilities, manufacturers and the R&D institutions is being carried out for a period of 4 years, and the experimentation for all the equipments, the insulator strings, the conductors, the towers are being done. So, very important for the ultra high voltage transmission. very soon we will be able to see the 1200 kV transmission in AC in the country. So, this is a representative tower which is used for single circuit and double circuit. So, such a big gigantic tower with lot of right of way clearances has to be maintained. So, lot of technology implemental aspect or advances in the high voltage and ultra high voltage transmission to cater the needs of the requirement of power and also domestic and also the industrial requirements. So, this gives some technical particulars of the 1200 kV transmission line in comparison to the 400 kV transmission system. You can see the electrical system data here, various technical parameters which are being given here. This column gives the details of the technical aspects for a 400 kV double circuit 4 bundle conductor, that is a 4 bundle quadrupole bundle transmission line, and the final column here it gives the details of the technical aspects for the 1200 kV single circuit line. A comparison could be made and the advantages could be summarized. Here in case of electrical system data, you see the nominal operating voltage being 400, here it is 1150 kilovolts, maximum system operating voltage is 420 kV, here it is 1200 kilovolts for a 1200 kV system. The power frequency withstand wet, that is during the rain condition, the insulation requirement is 680 kV at 50 hertz, here it is 1200 kV RMS. Switching surge withstand voltage requirement is 1050 kilovolts peak, that is a wet condition, here 1800 kilovolts peak is the required for switching surge. Lightning impulse or the basic insulation level required for 400 kV is 1550 kV peak, whereas for 1200 kV it is 2400 kV peak, and the minimum corona extinction voltage in case of laboratory dry conditions, clean conditions requirement is 320 in case of 400 kV, and for 1200 kV the requirement is 800 kV. So, 800 kV or 810 kV is the minimum required corona extinction voltage under laboratory conditions. So, the RIV or radio interference voltage measured at 1 megahertz under dry conditions could never exceed 1000 microvolts at 305 kV between phase to earth voltages. This is again same for 1000 microvolts at 762 kV phase to volt. So, at 305 1000 microvolts is the permitted, even at 765 1000 microvolts. So, how good is the hardware is very important. The conductors, the hardware, the corona control rings, the proper design plays a role here as the voltage level goes higher. The radio noise, audible noise have to be at the same level similar to a 400 kV or a 765 kV system. So, conductor bundles, what type of conductors? Here 4 conductors, that is a quadrupole 4 conductors, all aluminum conductor steel reinforcement, most type of conductor is being used. Here octagonal 8 conductors of ACSR moves are being used for 1200 kV. Earth wire, number of earth wires and size for 400 kV typically 2 numbers of earth wire with 7 strands of 3.6 mm dia of galvanized steel are used. Similarly, for 1200 kV again 2 numbers of earth wires with 19 strands of 3 mm dia are being used of galvanized steel. So, towers, what type of towers in comparison to 400 and 1200? You can see types of towers, either if it is a suspension type, type known as DA is used for 400. For tension use DB, DC and DD, these are the various types used for tension configurations. For suspension in case of 1200 kV tower type A is used, and for tension tower types of AS, B, C, D and E are employed. So, configuration either for 400 kV it is vertical configuration, here it is horizontal configuration of the towers. What are the electrical clearances important? So, electrical clearances, live metal, that is a conductor or the corona control rings of the conductors, the minimum air gap clearances have to be maintained is 3.05 meters in case of 400 kV, and in case of 800 kV it is a minimum of 8 meters, that is around 24 feet. So, the ground clearances are very important. For 400 kV towers, the ground clearance is 8.84 meters is the minimum ground clearance to be employed, and in case of 1200 kV towers the minimum distance is 24 meters, anywhere around 75 feet is the minimum requirement for 1200 kV. So, very important point. Insulator strings, the type of insulator strings which are employed both for suspension towers and tension towers are follows. For suspension towers, 120 mechanical strength, that is a kilonewton insulators of 2 into 23 insulator. 23 is the number of insulator, 2 strings of 23 are employed, double suspension, 2 vertical suspension consisting of 23 insulators in each arm are used, and for say case of a single V suspension we have to consider 320 kilonewton mechanical strength, again with 2 arms of 51 insulator each for 1200 kV are used. So, for tension 4 conductors of 160 kilonewtons of 23 insulators, that is a 4 into 23 parallel strings of consisting of 23 insulators, 4 into 23 employed. For 1200 kV it is 4 into 51. So, 204 insulators in one quadrupole string of 1200 kV. You can imagine, so 200 insulators, each insulator typically weighs around 12 to 15 kgs. So, you can plan and you can estimate the total weight of an insulator string including the line hardware, the yoke plate, the corona control rings near the tower. So, every important aspect, these are the things to be considered for the mechanical loading of the tower, the estimation of the tower, the height, the clearances, so on and so forth. So, now coming to HV DC towers, there is a difference in case of HV AC transmission line and HV DC transmission line. So, here the configuration varies with the load requirement, mechanical load changes here, the conductors are employed are different, and the tower configuration also changes depending upon the clearances. So, these towers which are indicated here are for the high voltage DC transmission system. So, we have earlier looked into the AC transmission towers. So, there is a design change in comparison with the AC transmission. So, this typically are used for plus minus 500 kilovolts. The details of the technical details will be looking into this. So, you see the technical particulars particularly for the plus minus 500 HVDC lines which you have seen here, the tower clearances, the tower details, the number of insulator strings, number of conductors which are being employed are given here. So, the conductor bundle employed in case of 500 kV plus minus configuration for HVDC transmission is again a 4 conductor bundle. You can see the 4 conductors in a bundle here are here. The 4 conductor bundle is employed with aluminum conductor steel reinforced either Bursimis or a lap wing conductor is employed with each conductor bundle spaced at 457 mm spacing. What type of towers and the span, again the type of towers for 500 kV system for HVDC transmission is suspension type A type of towers, or in case of a tension B, C and D are normally employed. For the normal span is 400 meters, that is the tower to tower distance used for the 500 kV HVDC is 400 meters. The electrical clearances from the metal part, that is the live metal clearances from the conductors is minimum of 3.75 meters. Then pole to pole spacing is 12.5 to 13.5 meters. So, that is the pole to pole spacing, that is one to other is 13.5 meters, and the ground clearances. So, minimum ground clearances from the conductor, that is from the conductor to the ground. This minimum clearances is used is 12.5 meters for a 500 kV transmission HVDC towers. So, for what are the insulators which are being used without for various configuration, they use a suspension type for towers, either V configuration, single V or a double V. In case of single V, 160 kilonewton and 210 kilonewton insulators consisting of two arms, one V is one arm, other side is one more arm, consisting of two arms of either 38 insulators of 160 kilonewton or 41 of 210 kilonewton are normally used. It should be 38 of 210 and 41 of 160 kilonewton. So, you have to consider two arms of this insulators being used. If for suspension for tension towers, again 4 conductor bundle quadrupole tension is employed. Here again 160 and 210 kilonewtons are insulators are used. In case of 210 kilonewtons, 38 numbers will be used, and in case of 160, 41 will be used. We have to consider that 210 is 38, 160 is 41 of 4 strings. So, 4 strings parallelly consisting of 38 numbers will give you 210 kilonewton for a tension of 500 kV plus minus HVDC towers. So, this is the technical particulars for plus minus 800 kV HVDC line. Earlier we have seen plus minus 500 kV transmission towers. So, now we have recently energized from Agra to Arunachal Pradesh 800 kV HVDC line, which can carry the power of 6000 megawatts. So, very important advances or the advancement in the high voltage DC transmission technology which has happened in the country. So, this plus minus 800 kV HVDC transmission line has following electrical system parameters. The system voltage is operating is plus minus 800 kV DC. The maximum voltage again is 840 kV for 800 kV system. The switching surge or a switching impulse withstand, that is for rain conditions or a wet condition, is 1850 kilovolts, and in case of lightning impulse or a lightning surge withstand voltage is 2250 kilovolts peak DC. The minimum corona extinction voltage should not be less than 880 kilovolts for 800 kV transmission, and RIV at 1 megahertz for 22 kV per centimeter conductor surface gradient under dry condition should not exceed more than again 1000 microvolts. So, the voltage level increases, the radio noise is again restricted to 1000 microvolts. The conductor bundle which is employed is again hexagonal consisting of aluminum conductor steel reinforcement. A lap wing is a 38 mm dia conductor, hexagonal is 6 conductors of ACSR lap wing conductor. So, towers type of towers employed in case of suspension configuration A, and for tension B, C and D are adopted for the 800 kV HVDC line. The typical span, that is a normal span from tower to tower used is between 400 to 450 meters, the towers the normal span which is used for this line. The electrical clearances, minimum metal clearances from the conductor to any of the other side is 6.5 meters. Then pole to pole spacing here is anywhere between 22 to 24 meters. The ground clearances is between 18 to 20 meters. So, 18 meters is a minimum and which is employed, and insulator strings which are adopted for 800 kV DC transmission are of Y suspension type consisting of 420 kilonewton mechanical strength consisting of 2 arms of 45 and 2 arms of 22. So, this is a Y configuration which consists of the V and suspension. Y can be assumed as V and suspension. So, V 2 into 45 and this I is 2 into 22. So, this number of insulators of 420 kilonewtons are being used for the tower, and in case of tension tower we have a triple tension, 3 conductors consisting of 420 kilonewton mechanical strength employing 64 insulators in each arm. So, 64 into 3 are used for the 800 kV line, transmission line. So, this is the line which I was mentioning. Very recently this line was energized, plus minus 800 kV HVDC. This is from Biswanath Chariali, that is in Arunachal Pradesh, and the line reaches Agra. So, Arunachal Pradesh to Agra is a line which is more than 2000 kilometers length and which carries a power of 6000 megawatts. So, very important advancement in the country which is transmitting the power at a very high rating. So, 6000 megawatts is the power capability where this line could carry, and it is being energized very recently. So, what happens in case of the towers or the transmission has to be carried out at various locations which are very difficult, like a normal flat conditions. So, again the engineering have to be looked into about the configuration, proper estimation of the clearances. These things have to be different in case if it is a mountainous area and the tower has to pass in between the mountainous rocks. So, that time the configuration do changes and you have to adopt a different type of technology for transmission of power. These are few examples which are being employed across the globe during the various locations, particularly in the mountainous part. This and in case if it has to pass through the sea, so that our configuration how it is being employed. So, these are few examples which are normally deviation to the calculations which we have discussed till now for the 765 or 800 for lower voltage levels. So, such cases a special design aspect have to be considered, and the estimation have to be done, and the configuration of the towers have to be thought. So, this again is the repetition of the thing which I have mentioned earlier, the slide which shows the importance of the various voltage levels. You can see here very important. So, from the 400 kV 765 kV single circuit, 765 kV double circuit, 500 kV HVDC, 800 kV HVDC and 1200 kV AC. So, comparison for the right of way in meters, you can compare 46 meters is the minimum requirement for 400 kV transmission. For 765 kV single circuit, a minimum requirement of 64 meters. For 765 kV double circuit, the requirement of the right of way 70 meters, and 500 kV DC HVDC is 52 meters, 800 kV HVDC it is 70 meters. So, not much of difference in right of way between the 765 kV double circuit and 800 kV HVDC, and in case of 1200 kV HVAC it is 90 meters is the minimum right of way. So, now we look into the power capability, that is the power transfer capability of the transmission lines, and now you can very clearly see the capacity where a 400 kV transmission system could carry is 600 to 700 megawatts is the maximum. If it is a 765 kV with single circuit, anywhere between 2500 to 3000 is the maximum power it can carry, and for double circuit 6000 or 5000, anywhere between two circuits, that is single circuit of 2000 becomes 5000 or 3000 becomes 6000. So, this is 5000 to 6000 is the double circuit 765 kV. What happens in case of HVDC? You can see that the power at 500 kV could be 2000 to 2500. So, the high voltage AC transmission at 765 kV, the power carrying capability is almost equivalent to a 500 kV DC system carries similar amount of power. That is one of the reason for long distance transmission high voltage DC becomes much more economical after 400 kilometers line length. That is where the advantages of going in for higher DC to transfer large chunks of power for long distances. So, HVDC becomes much more economical. You can see here in case of 800 kV, that is a similar comparison to 800 kV double circuit line. You can see 800 kV HVDC line almost could carry 6000 to 6400 megawatts. This is what the recently line which is coming from Arunachal Pradesh to Agra has been energized and which can transmit power of 6000 megawatts. So, in case of 1200 kV, again you can transmit the power 6000 to 8000 megawatts. So, this is how the information is very important. And what is a megawatt per meter? This again gives the idea for 400 kV it is 15 megawatt per meter. If you compare, you can see for 765 kV it is 65 megawatt per meter, and for HVDC it is 90 megawatt in comparison to the 1200 kV. So, these figures give an idea that HVDC importance, and going in for HVDC becomes much more economical. That is where for long distance HVDC is much preferred in comparison to the HVAC transmission systems. So, some developmental aspects particularly for transmission line towers. So, lot of changes are being happening, a lot of research activity is being conducted to bring down the mechanical strength and mechanical steel structure. So, composite type of materials are also being tried out for the high voltage towers, so that the weight of the material could be reduced and the tower economy, not only the construction, the mechanical load, the cost could be reduced. So, a lot of activity is also going towards this end for the development of fiber reinforced plastic composite material being adopted. So, research is in progress towards a special towers for a very high voltage and both for transmission systems. So, how to consider the tower loadings? Very important aspects. We have discussed about the conductor mechanical loads, the insulator strings, the wind effects, some of the zones where the transmission towers are being constructed. So, these wind effects for the tower loading have to be considered before the estimating the actual tower loading, apart from the insulators, the line conductors, several accessories, wind aspects. So, this gives an idea for the basic wind speed. Again, the wind zones you have categorized, the wind zones have been categorized under 6 different zones. So, this is the velocity which it sees that per second, that is meters per second, where it is given the figures starting depending upon the wind zone to the various locations, and the reference wind speed is typically given as VR being equivalent to VB by K naught, where K naught is assumed to be 1.375, and for designing the wind speed the factor VD winds is equivalent to VR, and K1 and K2 are the factors, K1 being the risk coefficient factor and K2 being the terrain coefficient factor, what type of terrain, whether it is a planar or it is being flat or it is a mountainous area. So, these factors have a suitable factors to be considered for the tower loading. Then design of wind pressure considered is 0.6 into VD and VB, which are specified for various zones. This particular values are assumed and the effect of total tower loading is estimated. And the loads due to conductor, earth wire and insulator strings have also to be considered. Again, this type of loads, whether the loads are towards the transverse load or it is due to the conductor and earth wire, or due to the insulator string, or due to the deviation of the loads because of the wind at that area, what type of vertical loads, or it is loads because of longitudinal compression, tension. So, several of these aspects have to be considered for the total estimation of the loads which the tower has to take in case of the regular operation and also in case of the overloading aspects. So, several of these factors which are very clearly defined, the PD being the design wind pressure at that location where the tower is situated, CDC and CDI being the drag coefficients because of the wind, L being the wind span, then GC and GI being the gust response factors, and D being the diameter of the conductor, and T being the design tension, and D being the deviation angle where the conductor swings. So, several of these factors have to be considered to estimate the actual load where the tower sees, and so depending upon the tower loading, unnecessary foundations have to be thought and estimated, so that several of these factors have to be considered for the foundation aspects.